1970s. Instead of following the usual practice of developing a strike aircraft from a fighter, Britain did the reverse, developing a fighter from the strike aircraft. The result was the Tornado F-3, also called the ADV, for Air Defense Version. In this role, the Tornado carries an advanced radar designed specifically for air combat. Instead of bombs and ground attack munitions, the Tornado carries the Skyflash air-to-air missile. The most remarkable fighter developed in Britain is the Harrier jump jet. The Harrier was not developed primarily as a fighter, but rather as a multi-purpose fighter and strike aircraft. It was designed to take off and land vertically. The idea behind the Harrier design is intriguing.
When the development of the Harrier was started, there was a great deal of concern about the ability of the Soviet Union to shut down NATO airfields. An airfield is a very big, totally immovable target. It has a lot of vulnerable points. It was felt back then that to have a few aircraft that weren't dependent on runways was a good insurance policy. And that basically was why the Royal Air Force got involved with the original Harrier.
This British idea proved popular with other air forces that had a similar outlook on the future of air combat. In particular, the U.S. Marine Corps became a firm supporter of the Harrier idea, and the Harrier has become the backbone of marine aviation. The Harrier has now gone through 2 generations of design. The latest version is the Harrier FA Mark II. FA is the abbreviation for the Harrier's missions, fighter, attack. This new version is fitted with an advanced radar called Blue Vixen. Whether over the skies of Europe, Russia, or North America, fighter aircraft are constantly being improved, thanks in large part to the revolution in electronics. But advances in electronics benefiting the current generation of fighters are not restricted to the fighter planes alone. Sleek nor fast, with speeds barely approaching Mach 1. They are called AWACS, for Airborne Warning and Control System. On the modern battlefield, what can be seen can be destroyed, and the AWACS can see electronically much better than any other aircraft ever developed. As we enter the age of information warfare, the AWACS has become not only the eyes, but also the brains of modern air battle, the computerized commander of the digital dogfight. In essence, Airborne Warning and Control System is an airborne command post. Air Force officers sit at consoles, monitoring the airspace around them for hundreds of miles. What has made this aircraft so important has been the advent of powerful computers. With all this digital information, the AWACS becomes the airborne brains of the dogfight. Like a coach, AWACS can pass instructions to each individual member of the team. They can tell them precisely where the enemy is located. They can tell them the best tactics to use. They can decide if the enemy aircraft needs to be attacked by 15 friendly fighters or only 1 or 2. The dogfight is no longer a contest of one-on-one, but a complicated team effort. Victory is decided by the team that has the best coach or commander. For nearly 7 decades, air combat has steadily evolved. In its early years, the accent was on improving speed and maneuverability. The classic dogfight pitted 2 fighters against one another, and the margin of victory was often a few extra miles per hour of speed, or a few extra degrees of turning ability. But the contest was decided by the gun, which had a range of only a few hundred yards. From the biplane fighters of World War I to the sleek aluminum propeller-driven fighters of World War II, speed and maneuverability were the ultimate technical capabilities desired by the fighter pilot. Recent innovations, like thrust-vectored engines, are being applied to today's fighters to enable them to achieve maneuvers that prior to thrust vectoring, they were incapable of performing. Thrust vectoring techniques vary. One method places paddle blades into the path of engine exhaust to direct the flow of engine blast. Another approach is multi-axis thrust vectoring. The key feature of a plane fitted with this type of thrust vectoring is the axisymmetric vectoring exhaust nozzle, or AVEN. The AVEN can be fitted directly to the aircraft engine. Powered by hydraulic engine oil, 3 actuators drive the vectoring ring to allow multi-directional flow of exhaust. While severe angles up to 60 degrees per second can be achieved, computer software-driven flight controls allow no more than 45 degrees per second. This versatility gives the fighter maneuver capabilities that were previously impossible. The other approach to thrust vectoring is used in this advanced technology demonstrator called the X-31. The X-31 was developed jointly in the early 90s by Germany and the United States to see how far fighter maneuverability could be expanded. By placing paddle blades in the engine exhaust and using advanced fly-by-wire controls, the X-31 achieves unprecedented maneuverability. Thrust vectoring enables the fighter to pull up to a 45-degree angle of attack, with the engine nozzles deflected upward to keep the fighter in the same plane of flight. Higher angles of attack, up to 60 degrees or more, can be achieved while remaining stable and maneuverable. The fighter can maneuver easily through thrust vectoring. It is able to move out of the plane of flight with no effort. Thrust vectoring not only increases the maneuverability of the fighter, but also increases its stealth characteristics, because, using its thrust vectoring, it is able to maneuver without its control surfaces moving. Hence, they do not deflect into the line of sight of a radar, giving the fighter's position away. The X-31 can perform maneuvers that would cause any other aircraft to lose control or even crash. In mock combat against a Navy Hornet, the X-31 emerged victorious 80% of the time.
You can simply put the command into the stick, and it becomes more and more severe in its maneuverability. You can literally almost make a 90-degree turn. Unfortunately, the pilot can't take that. So we're really at the limits of what a guy inside can go through. Turn him into a puddle of wax. You just can't get him to do that.
This high degree of maneuverability is not confined to experimental aircraft. Russia has pushed the limits of the possible in its recent fighters, especially the flanker. By using advanced fly-by-wire controls, the flanker can be made to perform this incredible Cobra maneuver, literally stopping in space. This would cause nearly any other fighter to fall hopelessly out of control. In this maneuver, the fighter rears up on its tail, its nose high in the air. For a few brief seconds, no air flows under its wing, no air through its jet engine. This is the classic recipe for a catastrophic stall and loss of all flight control. The flanker avoids these perils by superb aerodynamic design and state-of-the-art computer flight controls. Although the Cobra maneuver is a remarkable air show demonstration, its usefulness in combat is open to question.
The classic thing that you don't do in a dogfight is anything that actually destroys your energy. And in the case of the Cobra, you come out of that maneuver in a very predictable, slow, level flight regime. So that you may use it to try and squeeze a shot off at one adversary who is then going to shoot straight past you. But if there's anybody else out there in the sky, you're low on speed and low on energy, and you're a sitting target.
But the importance of maneuverability in air combat is being widely debated. How valuable is maneuverability when an aircraft can be destroyed at long range by a missile before a dogfight will even begin? The most important revolution in aircraft weapons over the past decades is certainly the advent of the guided missile. Although missiles have been in use since the 1950s, the early missiles were plagued with problems. These early missiles, using tube electronics or unreliable transistors, could not withstand the brutal environment of high-speed flight. Their electronics were literally shaken to pieces, and when launched, often failed. By the end of the Vietnam War, new solid-state technology made missiles far more effective. Malfunctions began to lessen, and missiles began to dominate air combat. The first clear evidence of this came in the 1982 Falklands War, when nearly all the air-to-air victories were scored with new models of the Sidewinder missile. But the clearest hint of the future came in the same year during the war in Lebanon. The Israeli Air Force used Hawkeyes like these to serve as battle managers for the fighters.